Hello everybody and welcome to this A-level chemistry video about alkanes. This is the next in our series about organic chemistry. We've had our introductory videos and now we're going to spend a bit of time looking in more detail at the different families of organic compounds. So in this video we're going to take a look at what alkanes actually are. We're going to have a slightly deeper look at fractional distillation. You came across this during GCSE. We're going to go a little bit more deeply into it. Then we're going to look at industrial cracking, which again will have been mentioned at GCSE level, but not very much at all. And finally, we're going to look at combustion of alkanes, including some of the problems caused by combustion. Okay, so first up then, what are alkanes? Now, alkanes are defined as being saturated hydrocarbons. I think this definition contains two words that require a bit more understanding. Now, a hydrocarbon is a compound that only contains hydrogen and carbon. And so, if it contains anything other than hydrogen and carbon, it quite simply isn't a hydrocarbon and therefore can't be an alkane. The word saturated is a little bit more complicated to describe, but in as few words as possible, the bonding in alkanes is single bonds between carbon atoms. And this is what makes alkanes different to alkenes, because alkanes contain double carbon-to-carbon bonds. Now, the general formula of alkanes, we came across general formulae in our introductory video to organic compounds, is CnH₂n+₂. What that means is if we know how many carbon atoms something contains, 3 let's say, that means that to work out the number of hydrogen atoms it will contain, we double the 3 to get 6 and we add 2 on and we get 8. And so C7, double the 7, we get 14, add 2, we get 16. And then last of all, C17, H, double it, 34, add 2, we get 36. That's just a few examples of formulae for the alkanes. The next thing to note about alkanes is how we name them. The name is derived from the number of carbon atoms contained in the alkane. So if there is one carbon atom contained in the alkane, the root of this word is going to be meth. And all alkanes end in ane, so this would be methane for the alkane. 2 carbons is eth as the root, so it would be ethane. 3 is prop, so it would be propane. 4 is bute, so it would be butane. 5 is pent, so pentane. And 6 is hex, and so that would be hexane. We've taken a look at how we name alkanes and what their general formula is and how you would work out what something's molecular formula is. But let's take a look at how we can represent alkanes. Now, I don't want to go too much into this because I cover this in another video about formulae, but these are displayed formulae for alkanes. And I've done the first 3 on here. And things to note about this, first of all, is that all carbon atoms have got 4 covalent bonds. So if I highlight them here, 1, 2, 3, 4 for that carbon atom. I could have picked any other carbon atom as well. They all have 4. And each hydrogen only has 1. Here we go, on here. The next thing to note about displayed formulae is to be really careful about showing the precise connection between the atoms. So carbon to hydrogen, for instance, it's really easy to get a bit sloppy and to not aim your atoms and your bonds correctly. Now, displayed formulae is good, but it is quite lengthy to do. So it is easier to write structural formulae, where you just list the atoms in order. So CH4, nice and easy for methane. The structural formula and the molecular formula are actually the same. This one, ethane, a little bit trickier. We have CH3 followed by another group, which is CH3. Then last of all, propane, trickier still. we have a CH3 followed by a CH2 followed by another CH3. So that is the structural formula of propane. And you can see that's much better than the molecular formula and almost as good as the displayed formula on there. There is no ambiguity, there's no doubt that what we are representing is propane. And last of all, the type of formula to have a recap of is skeletal formula. And skeletal formula for methane is very weird. It's just a dot, and I think that's unlikely to come up in an A-level exam. Ethane is a line like that, and propane looks like this. Remember, at each of the vertices on here, we've got a carbon atom like that. If you want to have a full recap of formulae, then I've done a separate video about formulae and about isomerism as well. I mention isomerism now because alkanes show chain isomerism when there are branches. So if you remember, I'll just do skeletal. That's butane in skeletal formulae, and then that is an isomer of it. And that means they're made up of the same atoms, they've just changed how they are bonded together. So they're both C4H10, but the one on the right hand side, this central carbon, which I'll just highlight with a yellow dot, that is bonded to 3 carbons, whereas in this picture, that same carbon, carbon number 2, is only bonded to 2 carbons, and the chain is longer. And so the one on the right hand side would be methyl propane, whereas the one on the left would be butane. And then there is one last extra little complication about alkanes, because sometimes you get cycloalkanes. And cycloalkanes, it sounds like we're talking about circles. We're not quite talking about circles, we're talking about rings. So this is alkanes that are in a ring. And so if we have the skeletal formula of, say, cyclopentane, we would draw something that looks like this. And at each of these points here that I'm making a yellow dot for, there would be a carbon atom and they would be joined to 2 hydrogen atoms. So in the structural formula, we don't show them, neither do we show them in skeletal formula. In displayed formula, if I just show the beginning of the displayed formula, each carbon in the ring would have 2 hydrogen atoms attached to it. Do you know, it won't take long. I'll just finish the whole molecule off so you can see it. Because one last thing to say about displayed formulae is that they're not as good as skeletal formulae, even though you don't show a lot of the atoms in skeletal formulae. But the reason that I don't think they're as good is they don't represent the angle between the bonds very well. If you have a look at this picture on the right hand side, this looks like it's approximately, even though my drawing isn't great, it looks like it's approximately 90 degrees on each picture. Whereas skeletal formula shows that the bond is actually a little bit greater than 90 degrees, or it should do. And that represents actually that the bond angles in alkanes is closer to 110. So the bond angle is 109.5. That is in the non-cycloalkane. It is a little bit smaller than that in a cycloalkane, but the bond angle in here, if I just draw it, there we go, that would be 109.5 degrees. More about that in the structure and bonding topic, which is totally separate to this. So that's all I wanted to say about formulae and isomerism, because I've done separate videos about both of those. Check those out if you want to refresh. Now to just cover a few physical properties of alkanes. And we're going to look at 3. We're going to look at polarity, we're going to look at boiling point, and we're going to look at solubility. So first of all, polarity. So polarity is how polar something is. So there are 2 ends of the scale here. There is polar at one end, which means it shows charge or regions of charge, and non-polar at the other end. Now, alkanes are almost all non-polar, and that's because the electronegativities of carbon and hydrogen are really, really similar. And so as a result of this, the intermolecular forces between the molecules in alkanes are very, very weak. They are the van der Waals forces. And the larger the molecule, the stronger the van der Waals forces are. And so, because of these non-polar alkanes and the weak van der Waals forces, the boiling points of alkanes are generally very low. And so a lot of these alkanes are gases at room temperature. Certainly the smaller ones are. However, as I said, the strength of these van der Waals forces increases as the chain length increases. And so pentane with 5 carbon atoms is a liquid because it's got a boiling temperature of 36 degrees C or 309 Kelvin. However, when you get to something much bigger, round about carbon 18, the alkanes have got such a high melting point that in fact they become solids at room temperature. And so the boiling points are very low, but they do increase. And so as the molecule increases in size, the boiling point increases. And so the larger alkanes are liquids, and then the very large would be solids. And before we move on to the final property, just a little reminder that as you get branching in alkanes, we end up with a lower boiling point than we would expect for unbranched. And this is because the intermolecular forces are weaker because the surface area of contact isn't so good, and so the van der Waals forces are not so effective. The final property of alkanes that I wanted to mention is solubility, and simply put, the alkanes are insoluble in water. And this is entirely down to the fact that they are non-polar molecules. Water is a polar solvent, and so polar solvents will dissolve things that are polar very, very well, and they will not be able to dissolve things that are non-polar. And so since alkanes are non-polar, alkanes will not dissolve very well. So non-polar substances don't dissolve well. Now, alkanes are very unreactive. And the reason for this is that carbon-to-carbon bonds are very strong. And the carbon-to-hydrogen bonds are strong as well. And as a result of this, alkanes won't react with acids, bases, oxidizing agents, reducing agents. In fact, really, they only do a few things. The main thing that they do is burn. So alkanes are flammable. And in fact, alkanes are our biggest source of fuels that we use in the world. So alkanes, probably their single biggest use is to make fuels. They are also used as lubricants. And what that means is they're used to reduce friction. So if you think engine oil or something like that, that is likely to be an alkane. They're also used as a starting material to make a range of other compounds, and that's one of their biggest uses in industry. They are used to make alkenes and halogenoalkanes and other members of other families. So for themselves, they're primarily used as fuels. Their secondary use is lubricants, but also to make other organic molecules. Now, the main source of alkanes that we have is crude oil. And in fact, crude oil is the world's main source of organic chemicals altogether. It's called a fossil fuel. And the reason for that is that it's formed millions of years ago by the breakdown of plant and animal remains at high temperatures and high pressures deep below the surface of the Earth, with generally a very, very low amount of oxygen down there. And because it's a fossil fuel, it is considered to be non-renewable because it forms at such a slow rate. Crude oil is a mixture of different alkanes of different lengths and of different branching. Most of them will be unbranched, but there will be a decent amount of branched alkanes as well. And you might have heard of different grades of crude oil. The different sources that we get crude oil from will have different compositions. So that means different amounts of the different types of alkanes. Crude oil doesn't only contain these alkanes, although that is the greatest proportion. They also contain small amounts of other compounds dissolved in the alkanes. These compounds come from other elements that were in the original plants and animals that went on to form the oil. And the biggest component is probably sulfur. And this sulfur can cause problems when we burn the crude oil later on. More about this a bit later. Now, the biggest problem with crude oil is that it is crude. And what that means is that it is unrefined. This big mixture is not very useful for anything. And so what we have to do is we have to separate this mixture out. And the process that we use for this, as the title says, is fractional distillation. Now, the first thing to say before we get any further into this is that fractional distillation is a physical process. And what that means is there are no covalent bonds broken. And that is a really common mistake in fractional distillation. There are no bonds broken at all. Let's take a look at the fractionating column, which is what we've got here, fractionating column. And the first thing to note is that we've got a furnace here, and the furnace heats the oil. And so what comes in at the bottom left is vaporized oil. So oil vapors. So that means gas. And what happens is these gases, this mixture of different gases, pass over into this tower. Now the tower, crucially, is cooler at the top and hotter at the bottom. And so these vapours that have entered the tower rise up through the column, passing through this series of trays. These are called trays, and this is a bubble cap. And they keep rising up through the tower until it is cool enough for them to turn back into a liquid and for them to condense. And so I've decided that my gas has got cool enough. And so it will turn back into a liquid, it will condense, that means, and it will collect in the tray, and then it will get tapped off. There'll be a pipe connecting the tray to the exit tube, and it will dribble out here as liquid alkane. And this will still be a mixture, but it will be a far narrower range of carbon atoms in this mixture. So at this height, maybe this would be of alkanes with between 12 and 16 carbon atoms in it. And that might be kerosene, probably we would call that. And so it's not pure, but it is far closer to being pure, and we've got some definite similarities. The shorter alkanes will rise further up the column because they will have lower boiling points, and so it needs to get colder before they can condense. And in fact, some of the alkanes don't actually condense, and so they come out of the top with alkanes with 1, 2, or 3 carbon atoms in it. And so, as I say, the shorter alkanes condense up here. And conversely, the larger alkanes, it never got hot enough to vaporise them, so they just dribbled straight out as a liquid. So the largest alkanes come out of the fractionating column still as liquids. They never even vaporised. And that fraction, and that's what we call it a fraction, would be maybe 70 carbon atoms in it. And that's usually called bitumen. And so I've filled in the names of all the different fractions that come out of the fractionating column at different heights. You can see that as we rise up, we collect the smaller alkane fractions because they have got lower boiling points, and then as we go down, we get larger alkanes. Just before we move on, the reason that we call it fractional distillation is because if this circle represented everything that was in crude oil, then each different fraction, this might be the gases, is a portion of the whole, and then this might be petrol. And then you get the idea. This could be kerosene, this could be diesel oil, this could be the lubricating oil, then we've got the fuel oil, and then this last one is the bitumen. So each one of these portions or fractions makes up the whole, and so that's why it's called fractional distillation. Connected to the fractional distillation is patterns. So the chain length is really important for predicting properties of the different alkanes. And so the fractions that get tapped off at the different heights, they are likely to have really similar properties. The fractions that are shorter, in general, will have a lower boiling point, which means they turn into gases more easily, or they turn back into liquids with greater difficulty, which is why they came out of the top as gases. They will also be more volatile. And volatile means it can turn from a liquid into a gas at normal temperatures. So that means at room temperature rather than waiting for it to get hot and reach its boiling point. They also get more flammable the shorter the alkane is, so that's obvious. That means it sets fire more easily. They get to be more runny, or to go at the opposite way around, they are less viscous. And viscous is a word that you'll remember from GCSE as meaning sort of gloopy and thick, like treacle. As a consequence of being more volatile, they're also going to be more pungent. That means they're going to smell more. And the last property is that they are less coloured. And so, flipping that on its head, what that means is the longer the alkanes are, the darker in colour they are. So if we compare bitumen, which is the stuff that goes on roads, that's obviously a black colour, to the stuff that comes out of your Bunsen burners at school, which is very short alkanes, that is going to be a colourless gas. So we've gone from something that has no colour to something that is really, really dark black colour. That's just to do with the length of the alkane chain. Moving on now to take a look at cracking, which happens on an industrial level in a variety of different ways. The reason that we have cracking is that we've got a high demand for some fractions of crude oil, for instance, naphtha or petrol, whereas we have a low demand for some of the larger fractions. And when supply doesn't meet demand, we have a problem because we can't provide the petrol that cars need, or we have too much of something that therefore nobody wants, and so it's not worth very much money. And so because shorter chain alkanes are far more valuable than the longer chain alkanes, we meet the demand by taking the longer chain fractions and breaking them up so the chain length gets shorter. And this is what cracking is. Taking the large alkanes and we break them up to make smaller alkanes. This is good because the smaller alkanes are far more useful, and so it's worth quite a lot of money. Compared to the larger alkanes that's worth a little bit of money, the smaller alkanes are worth quite a lot more. Even better than having the smaller alkanes that are worth more money is that another product of cracking is the alkenes, which we're not going to get into too much about today, but alkenes are worth lots and lots and lots of money. And so we've gone from something that's worth a bit of money, and we've turned it into something that's worth more money and a little bit of something that is worth a great amount of money. And alkanes are useful as fuels, but alkenes are used to supply all sorts of industries as the starting material to make a huge range of products, from drugs to paints and polymers and all sorts of everyday materials. So it's really important that we can turn these alkanes into more useful substances. So in general, large alkanes are broken into smaller alkanes. And so I've got an example of an equation here. I've got decane, which dec is 10. So that's going to be C10. It's decane, so we double it and add 2. So it's going to be H22. It turns into octane. Oct is 8, so it'll be C8. Double that, 16, add 2, 18. And ethene. Eth is 2, and it's an alkene this time, so we're just doubling it. And so this is the chemical equation for the cracking of decane to make octane and ethene. And they like to make exam questions about this. And so if they gave you this symbol equation, so we are cracking C18H38, and maybe in the question we're told that we make ethene, propene, and one other chemical, so we don't know what it is. And so we need to remember that ethene is C2H4. We need to remember that propene is C3H6. And now to work out what this other product is. Well, this is a matter of working out what atoms have already been accounted for. 2 carbon atoms in ethene, 3 carbon atoms in propene, and so that means we have got 18 carbon atoms in our reactant. The missing product must have 13 carbon atoms, because 13 plus 3 plus 2 makes 18. We do the same thing with hydrogen atoms. We've got 4 hydrogen atoms over here, and then 6, so that makes 10. There are 38 hydrogen atoms in the reactant, which means there needs to be 28 hydrogen atoms in this product. So even though we don't know what this hydrocarbon is called, we've worked out what its formula must be. Now there's 2 types of cracking that you need to know about: thermal cracking and catalytic cracking. As the name implies, thermal cracking needs a very, very high temperature, between 700 and 1200 Kelvin. So I'm going to write 1000 Kelvin because that feels really easy to remember to me. It also needs a high pressure. So not just a high temperature, it needs a high pressure as well. So something like 7000 kilopascals or up to that. And then what happens is the carbon-to-carbon bonds break, as we know, and then 1 electron from each pair in the covalent bond goes to each carbon atom. And so initially you get 2 shorter carbon chains. And this is what I've represented here in this green displayed formulae diagram. You can see we had 1 hydrocarbon at first. I've only drawn butane because I didn't want to draw all the extra carbon atoms, but this would be done on a really big hydrocarbon, in fact. And what we're left with at this stage is 2 molecules known as free radicals. And this dot here is an unpaired electron, and that is what a free radical is, something with an unpaired electron. And in fact, both of these are free radicals. Now, free radicals are very reactive as a direct effect of having an unpaired electron. And so they will react in a variety of different ways, and one of the ways will result in the formation of an alkane and an alkene. And you can see that what's happened is one of the hydrogen atoms on the right-hand side free radical has transferred over to the left-hand side free radical. And this had to happen because there weren't enough hydrogen atoms to make 2 alkanes. We needed to make an alkene. Now, I've drawn a really simplified version of this because what happens in industry is any number of carbon-to-carbon bonds could break. The chain doesn't necessarily break in the middle like I had for mine. We might also make hydrogen. Not only could we make hydrogen, we generally make a high proportion of alkenes compared to the second method. And so if we are looking to make alkenes to use in the ways that I've described earlier, this is really useful. We can try to control this reaction by limiting the amount of time that the alkanes are kept at these high temperature and high pressure conditions. And actually, it's as short a time as only 1 second, and this avoids too much decomposition of the hydrocarbon. Catalytic cracking takes place at a much lower temperature than thermal cracking. And this temperature is around about 750 Kelvin. The pressure would be a bit higher than the atmospheric pressure, but still considered to be low, and much lower pressure than for thermal cracking. The biggest difference, and obviously the source of the name for catalytic cracking, is that we use a catalyst. And the catalyst that we use is typically zeolites. Zeolites are actually a mixture of silicon dioxide and aluminium oxide. And the zeolite catalyst is organised in what's called a honeycomb. And the honeycomb allows us to use a small amount of catalyst for a big surface area. And this, of course, brings down the cost because you can get a big surface area for a small amount of money. This type of cracking doesn't produce so many alkenes. In fact, this type of cracking produces branched alkanes. Obviously, it produces the shorter chain alkanes as before, but it produces the branched alkanes, it produces cycloalkanes, and it produces aromatic compounds. Now, aromatic compounds, they're called that because they smell, but they're far more sophisticated than that. A really common aromatic compound is benzene. And we represent benzene by drawing a hexagon, like this, and then we draw a circle inside it to identify the special type of bonding that there is in benzene. But as with other skeletal formulae, at each of these points here, where I'm putting a yellow dot, there is a carbon atom. But each of those carbon atoms is only bonded to one hydrogen atom. Now, you can do catalytic cracking in a lab, and you might have seen an experiment like this. And in this experiment, you have a small amount of something like paraffin, which is a mixture of alkanes in the region between 10 and 20. And you have your catalyst, which is your aluminium oxide, which is kind of like the zeolite catalyst, only a little bit simpler. You heat the catalyst here, and what happens is the alkane gradually vaporizes here and moves across the catalyst where it gets broken apart in the cracking reaction, and then it moves down through this delivery tube into this water here. And what it does is it rises up through the water here as bubbles, and it displaces the water, and the water will move downwards, and we'll end up collecting a mixture of gas products on here. And they will mostly all be short hydrocarbons, so that's why they'll be gases, and there will be some alkenes in there. I said that there won't be so many alkenes, but there will be some. And you can prove that by checking with bromine water. And if you remember, bromine water is a yellow colour, and so you can get some bromine water into here, and you can add it to your gaseous product, and what you'll end up with is your bromine water will lose its colour. So the bromine water will decolorise in the presence of an alkene. If there wasn't an alkene, the bromine water would stay yellowy brown. Last of all, I should say that both methods of cracking produce mixtures of products, and these mixtures of products that are made are then separated by fractional distillation again. And so what you end up getting is you end up with fractional distillation in the first place to make your different fractions, and then you crack the fractions, and then you end up with a smaller range of products, but then you'll fractionally distill them again, and then you'll end up with far more refined alkanes or alkenes. And what we mean by refined in this context is they're very, very similar in terms of the length of their carbon atoms. Over here, we ranged from 1 and 70 carbon atoms, more than 70 maybe. When we get over to here, the variety in chain length will just be a few carbon atoms. The last thing that we're going to cover in this video is combustion. And combustion is a slightly fancier way of saying burning. And the things that we burn are called fuels, and a fuel is something that releases heat energy as it burns. And like I said before, alkanes are quite unreactive, and so really the main thing that they do for themselves is they burn. Now the shorter alkanes burn really, really well. They burn quickly, they've got a clean flame. And then there is a sort of a sliding scale that the larger alkanes have a far sootier flame. They don't burn very cleanly at all. So that's a contrast between the different lengths of chain. Now, in terms of combustion equations, if we take methane, which is a gas, it burns in oxygen. So all combustion equations have to have oxygen, and the oxygen turns into carbon dioxide gas, and it turns into water. Now, even though the water that's produced is a vapour, we write L in the equation because we always include standard state symbols in here, so we don't include it as a vapour. Now, this equation isn't balanced, and the reason it's not balanced is the oxygen and the hydrogen. We've got one carbon on both sides, but the oxygen's a problem. Now, a really big piece of advice, where you've got atoms in more than one compound either side of an equation, leave that till the end. So where you've got one carbon and one carbon, we've got 4 hydrogen atoms and we've only got 2. So I suggest we solve the hydrogen problem first. And to do that, we put the multiplier 2 in front of the hydrogen, and that gives us now 4 hydrogen, so tick for the hydrogen, and we can already tick our carbon. This then leads us onto the oxygen. This multiplier applies to the oxygen as well. So we've now got 2 oxygen in our water, and we've got 2 oxygen in our carbon dioxide. That, of course, adds up to 4 when we take our 2 and 2 and we combine them. So to do the balancing on the left-hand side, we need to put the multiplier 2 in front of the oxygen. If we look at this equation for propane's combustion, same idea, leave the oxygen until the end. We've got 3 carbon in the reactants, we need to have 3 carbon atoms in the products, and so we put the multiplier 3 in there. We have 8 hydrogen in the reactants, we need 8 in the products, so we put the multiplier 4 in there, because 4 times 2 equals 8. Now we need to move on and look at the oxygen. In carbon dioxide, we've got 3 carbon dioxide, so 3 times 2 gives us 6 oxygen. In water, 4 lots of 1 oxygen gives us 4 oxygen in total. 6 and 4 adds together to make 10. We need to have 10 over here, so to solve that we need 5 O2. Now, sometimes there's a limited supply of oxygen, and so instead of making carbon dioxide as a product, we might make carbon monoxide. Now, carbon monoxide is a poisonous gas, so it's really important to understand how this is being produced. And so we make carbon monoxide when there's a limited amount. If there is even less oxygen, we sometimes make just the element carbon in its solid form, and we call that soot. And that's the sort of stuff that you find on coal and up chimneys from coal fires. And so you also see this in a lab when you're using a Bunsen burner with the air hole completely closed on what's called the safety flame. And if you're using this to heat a piece of apparatus, such as a beaker, the beaker ends up with a black sooty deposit on the bottom, which comes off on your fingers, and you end up with the black powder on your hands. And so this incomplete combustion happens because we've closed the air hole, and so not as much oxygen is getting in to make the flame burn properly. I mentioned before that longer chain hydrocarbons don't burn so cleanly, and that's because there is less likely to be enough oxygen to burn the alkane properly when the chain is much longer. If we take a look at these equations aren't yet balanced. We're going to balance them in the exact same way as we did on the previous page. So we need 3 carbon on this side, and we need 4 water molecules, just exactly like before. This time, though, the amount of oxygen that we've got on the right-hand side is going to be different, because in 3 carbon monoxide, we only have 3 oxygen. In water, we still have 4 oxygen. So this time, our O2 only needs to add up to 7. And so on this occasion, we are actually allowed to put a fraction in front of the oxygen. This is one of the few times that we use fractions in chemistry. There are a few others, but fractions can be used in balancing equations, particularly for combustion reactions, because 3.5 multiplied by 2, of course, ends up giving us 7. For the production of soot, we still need 3 because we still need 3 carbon atoms, and we still need 4 over here. But this time we actually only have 4 oxygen in water, and we have 0 oxygen in soot. So 0 and 4, of course, makes 4, and so we only need 2 in our O2 in the reactants. And so you can see, if we start at the top, this was complete combustion where there was plenty of oxygen. We needed 5 oxygen for our 1 propane. when there was a bit less oxygen, only 3.5 moles of oxygen for 1 mole of octane, we made carbon monoxide instead. And then when there was only 2 oxygen molecules for 1 molecule of propane, we didn't make any carbon dioxide or carbon monoxide even, we made soot instead. This leads us perfectly on to look at some pollutants that can be made when we burn alkanes. So these 7 substances are the most common pollutants that you need to be aware about. We've already mentioned some of them. Carbon monoxide is a poisonous gas, and it's made through the incomplete combustion of the alkanes. In the same way, the carbon particles, sometimes called particulates, that can exacerbate asthma. So exacerbate means make asthma worse, but also it can be linked to other problems such as causing cancer. Carbon dioxide, which we've seen can be produced by burning alkanes when there's plenty of oxygen, that, along with water, is a greenhouse gas. And we'll come back to greenhouse gases in a moment. Sulfur dioxide, which, remember I said that alkanes sometimes have sulfur dissolved in them, sulfur dioxide is a contributor to acid rain. And that's produced when sulfur reacts with oxygen to make SO2. That's a nice simple equation on there. Nitrogen oxides, sometimes abbreviated to NOx because that can be in various proportions. They are most commonly produced in petrol engines because of the high temperatures present. You get the high temperatures when you ignite your fuel in a petrol engine, and nitrogen, even though normally it's very unreactive, because of this high temperature, it is capable of breaking apart and then reacting with the oxygen. And just like sulfur dioxide, nitrogen oxides are able to react with water, and when they react with water, that makes acid rain because both of these are acidic gases. The last pollutant is unburnt hydrocarbons, and most commonly these will be ejected into the atmosphere through the exhaust pipes of cars. And what they will do is they will rise up into the atmosphere and they will actually react with things like nitrogen oxides, and you will get something called photochemical smog. And what happens there is the unburnt volatile hydrocarbons react with the nitrogen oxides and they leave tiny airborne particles, which is really similar to the soot that we mentioned earlier. And that can interfere with the sunlight and it can give you a kind of a haze effect over a city. I want to finish this video by looking at a few of the effects of the pollutants that we've just mentioned in a bit more detail. So we'll start with sulfur dioxide. Power stations are probably the greatest contributor of sulfur dioxide into our atmosphere, and that's because they generate electricity by burning fuels such as coal or natural gas. These fuels, particularly coal, have got a large amount of sulfur contained in them, and so when you burn the coal, you produce the sulfur dioxide. And the sulfur dioxide, as I mentioned on the previous page, when sulfur dioxide reacts in the air, it reacts with some oxygen and some water, and we end up making H2SO4, which you will probably remember is the formula for sulfuric acid. When these gases are produced in power stations, they leave the power station through the chimney, which is sometimes called the flue, and we get these gases called flue gases as they leave the power station. So one method of trying to make this less of a polluting process is to use a slurry of calcium oxide, which is called lime, and then with water it's sprayed into the gas as it rises up through the chimney. And the calcium oxide or lime and the water and the sulfur dioxide react together to make something called calcium sulfite, which then reacts with even more oxygen to make a chemical called gypsum, or more technically calcium sulfate. Now gypsum is actually something that we can sell, which means we can make some money out of this process. It's used to make builder's plaster and plasterboard as well. Alternatively, instead of using lime, we can use calcium carbonate or limestone, which is actually a little bit cheaper, And a similar reaction happens. The calcium carbonate reacts with oxygen and it reacts with sulfur dioxide, and we end up making calcium sulfate and carbon dioxide. This is obviously a good thing because we are no longer releasing sulfur dioxide into the atmosphere, but it does prompt two follow-up questions. So first of all, in the first reaction, this was a good thing that we made gypsum because we could sell it. In the second reaction, we've got two issues. Calcium sulfate needs to have a further reaction to turn it into gypsum, so that's a good thing. We can still turn it into gypsum. But the biggest issue is that we're producing carbon dioxide in this process, and carbon dioxide, as we've already said, is a greenhouse gas. So for preference, you would use the first method because it doesn't produce carbon dioxide. All new cars that work with petrol engines are now equipped with catalytic converters in their exhaust systems, and that has to be the case by law. And catalytic converters are quite complicated, so I've just drawn it represented as a rectangle in here. And so what happens in the catalytic converter is the gases such as carbon monoxide, nitrogen oxides, and any unburnt hydrocarbons, they enter the catalytic converter having left the engine, and the catalytic converter is a honeycomb, as I've mentioned before, and the honeycomb allows for a very large surface area, which maximises the opportunity for collision between the exhaust gases and the catalyst, and it means a little bit of the expensive catalyst goes a long way. And this is really important because the catalysts that we use are really expensive things like platinum or palladium or rhodium, and these are very rare and so they're very expensive. And as the polluting gases pass over the catalyst, they actually react with each other and they go on to form less harmful products. For instance, carbon monoxide, poisonous gas, reacts with the nitrogen oxides, which can cause acid rain, to make nitrogen gas, which is a big component of our atmosphere anyway, so not a problem, and carbon dioxide, which is a greenhouse gas, so that's a bit of a problem, but it's not as bad as the carbon monoxide being produced. In this second equation, what you can see is the unburnt hydrocarbons, for instance octane here, react with nitrogen oxide that was going to be vented out of the exhaust, and they react together in the catalytic converter to make nitrogen gas and carbon dioxide and water. So you can see that the final, so if this is the exhaust over here, the final gases that get emitted from the car are nitrogen gas, not a problem, carbon dioxide, greenhouse gas, so that's still a problem, and water vapour. So that's a greenhouse gas as well, but considered to be less of a pollutant. Moving on now to take a look at global warming and the greenhouse effect. If this circle on the left-hand side represents the Earth gets warmed up by heat radiation that travels from the Sun. Now, the visible radiation from the Sun is able to penetrate the gases in the atmosphere, and that's what we've got here, the gases in the atmosphere. And when infrared radiation is emitted by the Earth, which is what happens next, as the Earth cools down, some of the infrared radiation passes out into space, but a portion of the infrared radiation is trapped by these greenhouse gases in the atmosphere, which kind of act like a blanket keeping the heat inside. And this is really important because the infrared radiation warms the Earth up, and without carbon dioxide and other greenhouse gases, the Earth wouldn't be warm enough to sustain life. The greenhouse gases are carbon dioxide, water, and methane, which is this last one, the smallest alkane. And water and methane are actually even more effective than carbon dioxide, but because their levels in the atmosphere haven't really changed very much in recent years, carbon dioxide is considered to be the greatest problem. Because since the Industrial Revolution, we've been burning more and more fossil fuels in industrial plants, and the level of carbon dioxide has been rising. Gradually, the Earth's temperature has been rising as well, and It's the common belief among scientists that the increasing level of carbon dioxide is causing global warming. This is because the concentration of carbon dioxide in the atmosphere is getting greater, and so the thicker this greenhouse layer of gas is, the greater the proportion of heat energy gets trapped and re-emitted back down towards the Earth. And so the more carbon dioxide, the more trapped energy, the more the Earth warms up. Now, there are a number of widely known effects of the increasing temperature of the planet. And so I won't go into all of those, such as the ice caps melting and sea levels rising. The one that is slightly less obvious is that if the temperature of the atmosphere rises, there will be more water vapour in the air. And since water is a greenhouse gas, if there's more of it in the air, we will end up with even more global warming, and so the problem will be getting worse. The very last thing I wanted to mention, because it's relevant to combustion, is carbon footprint and, most importantly, carbon neutral activities. You'll probably know that the carbon footprint is the total amount of greenhouse gas emissions caused by a particular event or organisation or product, and normally it's carbon dioxide that we're talking about, but really it doesn't have to be carbon dioxide, and we talk about carbon dioxide equivalent because there is methane and there's water as well. Now, the great goal of activities and industry is to reach carbon neutrality. Now, carbon neutral activities are activities that have no carbon dioxide emissions overall. That doesn't mean that no carbon dioxide is produced. It means that the carbon dioxide that gets released in the process, maybe through burning, be exactly equal to the carbon dioxide that went in to the process. The most simple example of this is, say, carbon dioxide going in during the photosynthesis as a plant grows, and then the CO2 released when we burn that plant. And so that is considered to be significantly closer to carbon neutral than burning alkanes. And it's something that we're very keen to explore as our use of fuels increases and we become even more conscious about our impact on the planet. Okay, that's everything in this video. I hope it's been useful. Next time we'll have a look at halogenoalkanes. Thanks very much. Bye-bye.